Alright.
Explain the new fancy seal full freshness. This lecture is.
Alright, so good morning, everybody. So today we're going to be talking on Tomasulo's algorithm and the parallelism that goes on to it. This should hopefully be a little bit familiar as you've gone through some of the areas, but we'll talk about some of the extensions. Now, Tomasulo came up with this algorithm in the 60s. I think he finally published it in like 67 or something like that. It had been used on the IBM 390 and things of this sort. But it didn't become super popular for a lot of other machines until late 80s, early 90s time frame. And one of the big things that came that kind of pushed it on was that as cache systems became more popular, the way in which you can be able to schedule and handle the fetches and the organization to keep the data synchronized becomes very helpful inside Tomasulo's. Plus, it's actually pretty independent of your pipeline structure on how you can add things in. So between different systems, it's a very nice, efficient way to handle how things work. So in that sense, it becomes very generic, which makes it easier and more efficient for compilers to generate good code and things of this sort. And also nice to be able to set up hardware. Now, this is in general, a three-stage system. Right? So, that goes on. You could, of course, adapt it to other situations that's in, but our main area, we're going to kind of imagine that the fetch is happening automatically getting pushed in. So I'm not going to list that as one of our areas. We're going to assume that that's there. And so it really just handles the issue part and then the execute and then the update portion as it goes on. And then there'll be a process that'll constantly be fetching and shoving it in, but we're going to have this nice little kind of table of the instructions on the queue that goes on. So it'll take care of that automatically for us. So as far as the execution portion goes, we won't have to worry about it. Now, there's three main units that we're going to go in. And there's a definite connection between this and the idea of scoreboarding. Now, the most vanilla version of Tomasulo's algorithm, we have the simplest thing to handle inside this that goes on. This is the instruction queue. This is kind of the brains of the operation, so I like to abbreviate it. It kind of underscores that idea. And we have the instructions, and then we can just have, on that basic one, what stage we're in. Right? So, has it been issued? Is it executing? And is it ready to update as it's going on? And these ones are just Boolean flags. Yes, no, it's going on. Now, it is possible to add extra features that go on and extra information at each of these stages. It's also possible to make this into a reorder buffer at the end where the answer gets placed back inside here. And we'll talk about that adaptation a little bit later on. But I want you to think about this. This is kind of minimal information, the instructions coming in. If you remember, we've talked also about branching and some of the branch predictors and tournament predictors and things of this sort. If you think about this queue, and we were talking about how you could do speculation with them and that, you can actually associate with this queue a branch predictor. And so now your instructions just get loaded in, and in addition to where is it inside completion, you can also have branch predictors and speculation and all kinds of other stuff associated with this kind of queue that's going in. All right. In addition to that, I like sticking the registers over here. So this is our register file. So we have the register, the value, and then we're going to have basically who is producing. So we're used to everything but this last stage. So I've got the register, and I can say, for instance, the value is going to be whatever would be stored in there. That's your typical register file. Then we add on this extra one, which is how we handle the register renaming. Right? which of the reorder buffers is gonna hold the actual thing that's gonna be produced by that register, or what that value would be from that register. So that's where the production value goes. And this is actually the key to getting things renamed, because if somebody has a destination that's going to be going to register 3, whatever instruction is doing that, I can actually put that instruction's reorder buffer that's going in, and then you can just go there to get the answer. So that means anybody coming on will know where to go to get the answer, so if they don't get the value, they'll get who's producing it. And by getting who's producing it, they've now handled any right after read or right after write type situations. That's going on. By having them handled, it also is automatically doing forwarding, which means it'll handle read after write problems as well. So by one simple little maneuver there, he handles our data hazards that go on. Now, it doesn't get it to you any faster, but what it will do is by allowing other things to pass and go around, you can at least fill up the dead space with instructions, provided there are instructions to do that in. The other thing that we've got is these functional units. So the functional units allow us to be able to have, and there's kind of a dual area to this. There's the reorder buffers that act kind of like a queue to them, particularly a priority queue. So I'll have my queue, and then that's going to feed into functional units. Like for instance, I could have like an adder. But I could potentially have multiple adders that are seen often. I could have ones that are going in, that's going into, a load store system, memory access. And maybe I decide that I only need one of those, make it easier to go out to my cache. So I can put different ones that are whatever things. I can make barrel shifters, I can make branching units. Whatever I need to do, I can build them. And I can put multiple units hanging off the queue. Now it is possible I could have a queue going to an adder, a queue going to an adder. But if you do it that way, it becomes kind of inefficient. And this is where the inefficiency comes in. How you stack up, if there's multiple queues that go to an adder, what if all of my flexible commands end up in one queue and the inflexibles end up in the other? You'll block the other one pretty quickly. And since these are priority queues, people can move around them. So essentially you kind of block one unit up. And then eventually you're going to run out of those commands and you're not able to move them around. So it just doesn't, it ends up not giving you as much flexibility because depending on how the order goes. Now if you've got one queue feeding in here, since it's a priority queue, I can grab the first one available and it can go to the first available system. So anybody can go to anybody. So, if there's a high priority command, you can handle it by increasing their priority amount. So imagine if I had a restaurant. We often use the example of these reorder buffers as a restaurant that's going in, and you can think of these units as if they're tables. So in this sense, we often call them reservation stations, each individual one of these. And depending on your order and everything else that you come into the restaurant, you get a place in the queue waiting for an available table. Now, imagine I walked into a restaurant and I'm like, oh, I got a party of 6. And they could ask me, hey, there's a table ready. Is your whole party here yet? Now, maybe my whole party's not here. So I can go, no, I'm waiting for another couple to arrive. Right? 4 of us are here, but 2 more are still coming. Right? They're not going to seat me necessarily at the table. I mean, they could. Some restaurants will, but in our case, you're not ready to go. So they just say, hey, you want to go wait over here, right? So I can go in the waiting area until my values come in, and that's actually what we hit when we get these reservation stations that say, do you have all your values? Are you ready to calculate? No? Okay, you can wait over here. Now, somebody else might come in, right? And they've got all their parties, so they're ready to go. They're going to get the first available table that's going in. Now, if there's 2 that are ready at the same time, you take them in. Who was the first come? Right? First come, first serve. But let's imagine that I had a high priority command, maybe it's an OS tag that comes with a higher priority. I can also allow a priority system to come in to give you a value, and you grab whichever one is the more important. Now, if there's multiple tables, that's easy to handle. But imagine there was different doors at your restaurant, and each door set a group of tables. Now it depends on which door you enter in. If you enter the wrong door, and that's the door everybody else has entered into, and there's just no tables available, even if there's tables in the other area of the same restaurant, but you didn't enter the correct door, you're now going to be sitting around until it's available. So you might get very inefficient load usage. So that's why we don't like to have, multiple queues to multiple things of the same type. It's much better to have them kind of fit in one area. Does that make sense as it's going in? Okay, so I've got all those kinds of units that's going on now. The data, and then we want to think, what type of stuff do we actually want to know about this? I need to know what the actual operation is that's going on. Right? So I need to know I put, adders there, but it could be a generic AOU. Could be an adder, but even if it's an adder, is it add or subtract? If it's a generic AOU, I could get all kinds of different operations out of it. Right? I could have logic functions, be doing shifts. Right? So I need to know what that operation is that's going on. Think about what you need to know in order for something to go. It would kind of be helpful to know, is it already inside one of the units? Right? So that's what we often call busy. Right? Is it calculating? Because when you look through them and you see all the values are available, you're going to want to execute it. What if it's a multi-cycle operation? Now something like AND, a logic function like that, is going to be blindingly fast. It'll be done in less than one cycle. But what if it's multiply? Right? That could easily take a bunch of cycles in order to be able to get a good answer. So depending on how long that's going to take, I don't want to keep reissuing it, if that makes sense to you. So busy lets me know it's already in the queue, so I won't reissue it. It lets me know, hey, that's been taken care of. Right? It's a 1-bit flag, so it doesn't take a lot of room. Now we've got the two V's, VJ and VK. This is just the value, right? And that's the first value, right? JK, just think in order. So if I was doing subtraction, it would be VJ minus VK. So those are the two values. Then the book and the original algorithms likes to use Q. In some of my notes, I like putting S. And here's why I change it. Because being dyslexic, I hate names that don't mean something. Like I can look at V and go, it's value. Right? What's the value I'm calculating? So I find that one memorable. Q. Right? At least with S, I can say source. Right? You could use P, who's producing it, but Q. Right? You have to go back to kind of remember this stuff was programmed in the 60s, where standard programming languages, you had up to 2 letters for your variable names. Right? They literally would not recognize more than 2 letters for a variable name. So when you had important variables, you had to do them in one, and so like for this one, if I wanted, you'd think QJ would actually have been its name that's going on. Now, if you happen to use a letter somewhere else inside, how you index for your for loops and all kinds of stuff like that, that's going on, it'd be very easy to run out of letters. So you might just be stuck getting a weird letter because you had no choice. And so in the 60s, that was extremely common. I just don't want to be stuck with a really bad name.
Do you think because I hadn't thought about it, but do you think Q was actually reference to like Q? Like Q?
No, it could be a reference to Q, which element in the Q was it coming from? So, it could be, because it's a bunch of Qs that's going in. I honestly don't know where and how he picked it. There's probably somebody out there. It never was that big of a thing to go on. I just never liked it.
Yeah.
right? It didn't appeal to me, and I had thought about the idea with Q, but it's, I don't know.
It feels generically truth table-ish.
Yes,
Yeah.
Flip-flop.
so,
Yeah.
you know, it is what it is. The other one you'll often see listed is A. Now, this will appear mainly inside depending on what your system is. A is for address. It'll only appear on the load store side, but if you think about it when I take these, the values you might do is probably going to be who's going to do, like think if I was doing a load, right? So I might have like, for instance, load word to register 3 from offset 4 from register 2, right? Fairly typical command. Now think about what this means. This means go out to memory location 4 plus register 2 and stick that value into register 3. Kind of point in generic computer science-y areas. But that means I have to calculate this, and then I have to do the memory operation. But it has to be done in one fell swoop. Now, when I do this, this is my first step, and then that's my second step. Where do I hold the intermediate value? A. Right? A just gets this, gets stuck into the spot.
Now you say A is only included if you're doing that type of memory operation, but do you have to either reset it or make sure that it's set to all zeros or something whenever you're?
So think about each one of these as one row inside this.
Yeah.
Right? So if I'm going to a load store, I'd have the whole
So
thing.
there's some default value which means don't do anything. Okay.
Right? But if I was doing this for an adder, I wouldn't build it, honestly.
Okay.
So, was the camera okay?
I thought it beeped, so I.
Yeah, I heard something beep.
Yeah,
That's
was
what
it
it was.
your phone or something?
Oh, I don't think so. That's always.
I just didn't want to, I want to make sure it didn't quit.
Well, yeah, they were filming a bunch of things yesterday. I don't know if they offloaded them, so I was
Okay.
worried. Maybe we were out of memory. Okay. But it makes sense, and I mean, you could theoretically add some other stuff that's in here. Now, if we can, I want to give kind of a generic overview, then we can run through an example of what's going on. Now, I've got a whole bunch of units here, and the question is, how do I send stuff between them? When I get an answer that comes back, who needs to see it? Right? So say, for instance, reservation station 1 here is producing a value. Who wants the value from reservation station 1? Could reservation station 2? Might.
Yeah.
What about reservation station 3? Could it? It could.
Yeah.
Could any of the reservation stations? Any of them could. Could any of the registers?
Yeah.
It might. If we had a reorder buffer, which means the answer has to go to here it might have to go there, right? So theoretically, the result from any particular unit might have to go anywhere. Now, I don't want to run wires from everything everywhere. That's going to get gigantic. So we just have a bus that kind of reads around and lets anybody who needs to access it, access it. We call that the common data bus, because it's common to everywhere and it holds data and it's a bus that goes on. Now, imagine I've got 5 functional units. Is it possible for all 5 functional units to finish at the same time?
Yes.
So what would happen if 5 functional units want to ride on the bus?
A need for arbitration.
Yeah, I mean, only one can ride on the bus at a time, can't it? So that means one writes in that cycle, and then the next cycle, one of the other 4 has to go. But it's theoretically possible that while I'm trying to drain that queue out, other ones that had finished could have run another command, because it could be a really short command, and might re-enter back into the queue. Now, that means I can produce at basically the rate, or things can finish at the rate of however big that common data bus is. But that could theoretically slow me down and could backlog stuff. So the reason you might want to be able to store a result into here is that it allows you to keep producing values there and allows it to going, and then it drains out as fast as it can. So that's why you might want to have, you know, a result field off of there. I could also have this one just directly communicate to here and put the result in the reorder buffer, and then this one sends them out. So that's one way I could handle it by having that extra field, and that would allow, instead of this unit having to hold its value until it sends and then it's clear, it allows me to start the next instruction while it's waiting. And that just kind of pushes further back, where does the backlog happen? But sometimes you might have a couple quick commands that are now backlogged. Might be nice to start some longer commands. And then it kind of, that time gets hidden by it. Does that make sense? Now, could I make more than one data bus?
You could.
I could make 2 data buses and send it everywhere, which would allow 2 instructions to finish at a time. Would that potentially cause any data hazards?
I'm thinking you're okay.
I am okay.
Yeah.
How do I know I'm okay?
Because if they've already finished,
The algorithm's kind of taking care of it.
yeah, if there were any issues, they've already been addressed.
They've been addressed because the reorder buffer just tells it who to listen to.
Yeah.
And if I'm not supposed to listen to you, what do I care?
Yeah.
It's just allowing you to shout out your answer faster. Could I make 3 common data buses?
Probably so.
What? I mean, could I make N of them?
It seems like
I
it's going that
I
way.
can build as many as you want. Is there a certain number of data buses that will cause me never to have a problem?
If you had as many as you had devices that could produce a result.
What if I had just, what if I had N devices that could produce the results and I did N minus 1? Can I avoid all problems with that?
I think so.
Let one of them wait, let everybody else go or
Right.
something.
See, I could probably get rid of a lot of problems. The likelihood of you hitting one is going to be pretty rare. But is it theoretically possible for everybody to finish?
Yeah. It should
Yes.
still be, yeah.
Right? So I can't prevent all things. Now, you can look at that and go, it's not going to be a big deal. That I would agree with you, right? Could I make one that kind of causes a weird backlog so it might jam a bit? Yes, I could make it better by allowing you to store results and allow things to keep executing. I can do a lot of little stuff to go. But unless you build as many data buses as there are functional units, you could end up with a conflict. Right? But the more you have, the closer it gets to the number of units, the less of an impact it's going to have, right? So there's benefits that you handle them. What's the problem with building a ton of data buses? Then why don't you just build one for everything?
Wires.
It's expensive.
Yeah.
It's expense, it's heat, it's space
Area, yeah.
that goes on, right? So what if I only, say I build K common data buses, but I usually only use less than 1/3 of them, right? If you think about my utilization of the bus, if this is time and this is, how many commands finish, right? You're probably gonna have some kind of steady state value. You might have momentary shots and some dips, right? If I try to make sure that I've got enough to handle here, so that you never run into a problem, that means most of the time, you've wasted
Yeah.
resources. And those resources at this point could have been used to do something else, which might have increased the production and overall would have helped me a lot more.
More functional units, yeah.
So this is one of those areas that goes on. It might be better to actually make it sometimes wait.
Yeah.
What's that trade-off that goes on? Well, this is why you have to do modeling and simulation. And the question is, what's the order in which these things finish and everything else? Well, that gets into all kinds of stochastic process. Right? So you have to do simulations and situations and see what's going to typically occur that goes on and where are you going to tolerate. It's a trade-off. And this is where it really becomes engineering. And engineering is all about trade-offs. Right? I trade off this for that. If it was just build this better and it's solved, then it wouldn't be engineering. That's more of a physics type problem, right? They're just asking what is out there, what can be done, how to describe it. If there was no trade-off, then you would just be doing a better job as it goes on. And engineers will do that, but that's not where you get into the practical situation of engineering, which is really you've got competing constraints and you have to get the best solution. So I would argue that optimization is really fundamental to the engineering way. All right, so that's kind of a trade-off on how you pick on those. There is no solid solution to what that is that goes on. What about on the other end, when I go to issue things? Typically what we'll do is we'll issue one instruction at a time as it goes in. Could I issue more than one?
With some work, yes.
Huh? I mean, ideally, if I want to get parallelism, if I'm issuing one instruction at a time, over a long run, can I have more than one instruction finish on average?
Yes.
For periods of time, but for a long period of time, what's going to happen?
Probably still about one.
If you think about how many things come into the queue, if for 10,000 cycles, I issue one instruction per cycle, right? You're going to have 10,000 instructions went in. If I look at about the same period for finishing, depending on how many cycles it takes to finish things, and maybe it takes up to, 10 cycles to finish an operation or something, you're not going to have anything that's more than 10 different from the original. So over 10,010 cycles for the stuff to finish, you've only got 10,000 instructions to deal with that's going on. So you're limited, in the end, your rate of completion is going to be limited by it. Now for a short period, I can of course get a spike. I mean, if I pick the right spot here, I can get what looks like a tremendous benefit that's going on. But once I take a look over a long average, law of large numbers is going to start coming in, and I'm going to be limited to being proportional to my input rate, because that's just what you have. Does that make sense? So ultimately, I have to get to multiple issue. Otherwise, I'm going to be stuck at a performance rate of basically 1 that's going on. Right? I mean, I can get some appearance by figuring the inefficiencies of where a pipeline would handle it, but pipelining already does that. So if I assume I've already got a pipeline system, what can I add with this? Well, one nice thing about this system is it's not bad actually for handling a multiple issue type instruction, because if you think about it, if I'm going to issue 2 simultaneously, particularly if I make sure they're not going to the same unit, it would be much easier to issue 2 things to 2 different units. Now, what would you need to know if I told you I was going to issue 2 instructions at once? Right? Instruction number 1, instruction number 2. What would you want to know about those instructions to say that it's safe to issue them?
Do they need to be free of the hazards mutually between them?
So that's where the issue comes in.
Okay.
What's going on between them? Because things before it, I've kind of already resolved out, the system handles it.
Right.
Things after them
Right.
will get handled when we get to those things. Right? So now the question is, how do I figure out what's going on between them? Because do I have a mechanism that's looking at something that's happening simultaneous?
Yeah,
Right? What if this one wants a result from there?
yeah, that's kind
That's what
Okay.
the rest of the system does for you.
That's what
But
the rest of the system
now
does,
you're-
but it's happening at the same
Right,
time.
right.
So this one hasn't been recorded yet.
yeah.
So, can I handle things that have dependencies? I mean, obviously, if I have 2 completely independent instructions, I'm okay, aren't I? So I can make a compiler that just says, hey, you can stack them in as long as they're completely independent. So that's, I think, would be obvious and trivial. That will work, no problems, as long as you can guarantee it. And we could say it has to meet that requirement. And if you don't meet that requirement, you're in trouble. And then I just bundle them together. Could I handle ones that actually have dependencies?
I think you could.
You can.
Yeah.
It's, because if they occurred in sequence, there would be a certain outcome in the system anyway. And if you can just figure out what that outcome is combinationally at that time, you can still.
So there's a couple ways that I can handle this. Let's talk about some of them that goes on. All right? Can I, within a cycle, actually even still have a hardware ordering? Let's consider the first most obvious way, I think. Can there be an order in between? What if here's my clock pulse. Could I handle number one, handle number two?
For the two-issue kind of case.
Yeah. So I can handle a two-issue case in this way, and I could force it to finish. Now, this is gonna run into some timing things, I gotta make sure this stuff works. But for a simple first case, if I want to go to a two-issue system, I could handle that pretty trivial. I really don't need any extra hardware, I just need to make sure it's fast
It's a time.
at this point that goes on. Okay? So some of the early systems did exactly this type of thing, and this was also done inside pipelines when they would go in, and they would just, in order to make them small enough that I could do this, they would divide the pipeline stages into different little subunits, so they're all smaller. So like issue would be a two-stage thing. There'd be one to collect all the data together, another one to see, is there an available unit to put them on? So we'd first find, is the unit available? Great. Once I found it's available, I'd shove it on to get the data to that unit, and the next one could come into it, and I can now handle it in a partial step situation. That's obviously limited. I can't go too much further, right? Can I go further than this?
Another clock or something.
So I can technically get to 4, because I can do a phase lock loop and I can have a phase shift that's going on. And by having that phase shift, I can partial step it. And a phase lock loop will keep the drift off and things of that sort. If you actually look at like FPGAs, they actually have these clocks available. So when you have a base clock come in, they will also handle a phase shift at 90 and 180 and all kinds of other stuff, depending on where you want to trigger it off. So they will have actually available to you multiple clocks, and you can actually set, you can even up-step or down-step the frequency on them. So some units operate off a slightly different clock speed. So there are some things I can do with that. But what do you think? Can I handle 16 issues simultaneous?
It's gonna get dense eventually.
Yeah, I mean, eventually you gotta slice it so small, it's gonna be really hard to get the gates to work out and everything else. So at a certain point, you're gonna have to bite the bullet and move to truly parallel. Alright? Now, how can I handle truly parallel? Let's say exactly simultaneous now. So now I can't play my game, right? Or maybe I do that in other sub-step areas. I mean, it's a viable area. If you just got a small number that's going, it's actually a good idea. But what if I wanted to go exactly simultaneous?
I think that's where you need to sort of do that business of figuring out what the outcome would have been if you'd done them sequentially.
So what if the compiler knows what's going on, the compiler knows the dependency. So what if it takes your instructions and it packs in instruction number 1 and instruction number 2, and I could, even if I wanted here, have some supplemental info that's available to me on how are they related. Is there any dependencies and things of this sort? So now you can issue them as if they are, and this info will tell you how to reset those flag areas. So now you can gather all your data. The resolution of the problem is already there, so it can update it based on what's in here. I'd have to do a little bit of extra logic, but it's already worked out the problem. So I know I'm not looking for a problem, I'm just making sure that the updates specified in that field go on. Would it work? Absolutely. Could I pack a bunch of instructions?
Yeah.
Yeah. As a matter of fact, some of the Intel systems did this exact thing. The most common situation was 3 of them that were packed in. And what they did is each of these were, you could handle, for instance, like a 40-bit instruction that's going on. And you had 8 bits that's going on. So that gave me 128 bits. Nice multiple of 2. So I could handle, a pretty nice packet of instructions, and those 8 bits would have the information for what's the dependence. This one is always completely independent of the others because it's the first inside the block. You only have to worry about dependencies from 2 to 1, but for 3, you have to worry about dependencies on 1 and 2. Now, this idea of being able to pack things into a larger instruction with sub-instructions in it, very popular in the 80s and has kind of reappeared starting again in the early 2000s. So this is one of the tricks that was used. This is called VLIW. Very long instruction word. That's why you get very long instruction words, because you pack a bunch of other instruction words inside it. So now it's one really big one, but I can obviously make this large, and I can handle that, and I can do a whole bunch of parallel executions now. I mean, just think of this one. I can get a parallelism up to 3. Now, I can go higher. I mean, if I did this and that, I could get up to 6. So on. Now, could I make it even bigger than 3 inside here?
In theory.
Yeah, in theory, I could go a lot bigger if I wanted. So people do examine how efficient these go. And people have tried systems that can handle up, at least theoretically, up to, commonly 32, 64, things like that. It goes in, some even up to like 128 on some simulations. What do you think is, for a good piece of like engineering code that might take a bunch of room, how much parallelism do you think you can extract out from them? How many parallel instructions launched?
I'm thinking it's gonna be pretty small, maybe 4, something like that.
Sound reasonable, 4? I see some kind of like.
It's the thing we don't have yet is necessarily, because that's a sequence, right? We're going to execute all of those. It's, the problem is where the branches pop up, and then what do we do with those?
So, yes, you actually, and makes me happy, right? So that's where a lot of the issue comes in. How big is that structure that goes on? How large is your loop? So a larger loop is going to actually be easier. Can I make the loops a little bigger?
Well, that's pretty.
I could unroll it, couldn't I?
Yeah.
So in loop unrolling, so I can take some of those other techniques that were software techniques now, and I can make them a little bigger and start packing them in. Now loop unrolling can run into issues based on loop carried dependencies, right? I mean, that's where we get the GCD test and all that kind of stuff we talked about. But I can handle that. Is it pretty, do you think it's fairly safe to assume I could probably unroll once, at least commonly?
Often, maybe better than 50% or something.
Yeah, so it's pretty common I can unroll at least once. I mean, it's not like a guarantee, like you can say, just assume you can. But if we're just talking ballparks, does this sound reasonable? Because before we go and try something, you should convince yourself that this is a sane thing to do. Because if it's not a sane thing to do, you shouldn't try it. Right? So, fairly reasonable to assume I can unroll once. On average, branch instructions are about 15 to 20%, which means your typical loops have about 5 to 6 instructions in them. Like I can often unroll at least once. You're looking somewhere around 10 to 12 instructions inside a loop. So your efficiency edge is going to happen at the edge of those branches. So you typically see under 16 is pretty normal. Somewhere from 8 to 16 is about where the efficiency goes. So it's a little bit more than you might have expected that goes on. It'll vary by your code. If you have a code that has, like a very tree structure or whatever, there'll be portions that become pinch points that goes on. And that becomes kind of a bigger issue. And we'll deal with how we can handle some of that stuff later on. But at least on this edge, it's reasonable to assume I could probably get a fairly good pack that's going in. On other stuff, I could have no ops or other types of things that just get excluded, and I could actually even have flags here that say just don't even count those, which means it would just lower my instruction rate of submission. But then, whatever your rate that you're sticking them into the queue is, in some sense, on average, kind of determine the rate that you can finish them at. It becomes crucial to that area. So if you've got a certain number of pipeline stages and an average amount you can issue, that multiple is what benefits you're going to get over in a completely unpipelined, unparalleled system. And so if you figure 3 pipeline stages and maybe 3 of these things, I can get up to the 9 times speed up over an unpipelined, un-Tomasulo machine.
So I have a question about
Sure.
those last 8 bits in that very long instruction word.
Yeah.
So the purpose of that is just to say, so like for example, for instruction 3, those 8 bits need to say whether it relies on instruction 1 and or
Right.
instruction 2, right?
Because in general, I mean, figure that these are just adds for the sec, right? So instruction 1 here could be, you know, add, right, destination R3, R2, R1. When you get to instruction 2 here, it could be an add, and it could be R4,
And R3.
R3, whatever, R2.
Sure.
Right, so there's a dependence here to here. I'd have to say, these are my 2 sources. Those 2 sources could be dependent. So I have to have at least 2 flags to say whether or not this or this one is dependent on something from one of the earlier. Right, at number 3 here, it has 2 sources, and it could be dependent on this one or that one. So this one only needs 1 bit, it's dependent, it's not. This one needs 2 bits.
Right.
It's not dependent, it's dependent on 1, it's dependent on 2. Right, that's going on, so that takes 2 bits per field.
Okay.
That's going in, you can pack those a little more efficient as you go on.
It
But
could get pretty big once you got to.
as you keep adding things,
Yeah.
right, giving you the information on what's going on is gonna start requiring more and more bit information about those crossings. Now, to handle these areas, and you wanna think a little bit about this, can I stick any instruction in any field?
Hopefully.
Can I put 3 branches?
Yeah, see, that sounds kind of sick.
I should probably not allow that, right? Because really, I mean, there is a little bit of an ordering implied inside the word, but that becomes a little ugly. So there are some limitations to go. This is true with multi-pipeline systems. We usually limit 1 pipeline will handle memory, right? We often have 1 pipeline, and it could be the same one that handles branches. And the other, usually whatever's added on becomes supporter areas that are limited, because I'm concerned with memory also, because you get too many, if I do a whole bunch of loads in there, you've only got so wide of a bus going out to RAM,
Yeah.
right? So you get too many things there, you've just created a pinch point, right? So you don't get any benefit from it. So your benefit comes if things are coming in at a nice even rate. So we kind of want the compiler to try to level things for us,
Right.
not to just throw a bunch of junk. So ideally, we do want to have some type of limitations on the type of operations that do go inside there, just to make it a little easier on us. And that's true not just with a Tomasulo's machine, but even with parallel pipelines or hyper-threaded machines. There's a lot of varieties that go on. But a bunch of them use VLIW. This is true, I mean, you'll see stuff even inside GPU communities and stuff that will take advantage. So this is really helpful because the idea, this is one of the ways you can let a compiler send you information. And by packing them, it's also sending you information, which ones are more compatible, to allow things to go quickly. And that lets us resolve answers fast, which means we can issue more in parallel. And that's where you get the really big speed ups. And all that comes from this same set of intuition that goes in. Make sense? Okay, so I've got a bunch of these type of examples that are inside the online notes. So I just want to kind of walk us through what's going on with these. And you've done at least this stage, and I think you're working on this stage. You might even have.
That was the last slide.
That was the last one you just finished. So, you know, this is the only one that's kind of left that's going on. It's happening. This one is really easy. But what you want to think about for each one of these, when a command comes in, let's just do single instruction at the moment, because it's easier when we're walking through. What's the process of what needs to happen? So let's take my, whatever I had there, I had to add R3, R2, R1. It needs to send out, it notices I've got the adder, so it's going to want to check to see, is there room inside the reservation stations? So if you notice when we built these reservation stations, one of the things that was allowed was you could ask, and it would say whether or not the queue was full or not full.
Right.
That was going on. That's to support this function, right? My main instruction queue is gonna see that ad, and it's gonna send out a thing to say, do I have room? If I don't have room, it's not gonna do anything, or it shouldn't do anything. So there's gotta be a connection from here to here just to be able to send a request that's going on. Now, these ones here, all three of them, need to be sent to the register file. Why all three?
Well, one of them is going to get a value.
So normally we only send two. Right, if you look at the MIPS pipeline
Those are
stuff,
the ones that-
we send two to get the values, and the other one, we usually put through a series of buffers, so it gets buffered, and then the address doesn't arrive until the data arrives, because you want the data and the address to arrive at the same time to know where to write it to. Not true here. Right? So that paradigm, out the window. Why?
We need that, who's producing it value.
Yeah, that's what sets up, that's our whole trick to avoid this, is otherwise that stuff is hidden. And it's actually when we send those things down the line, if you look at how forwarding units go, they try to intercept that signal and look at it to do comparisons. And that's how forwarding units go. Well, this takes the next logical extension, it just sends all three, it puts it in the producing, and it will naturally forward at that point. So when it goes into here, it sends all three of those. And then this unit will have two that it sends down. That says, here's your value. Now, might this unit need to know, if I do this all simultaneously, right? I can send this to say, do you have room? And I can simultaneously send these and it sends the two values. What if this is full? Does that need to know?
It needs to know that the issue is not going to occur.
Why? You're right. Why?
So that it doesn't commit a producing value to the
For register
destination
three.
register. Yeah.
Right? Because if it didn't get submitted, there's nobody who's ever gonna clear the flag because that unit
Right.
doesn't exist. Right? Now, it also does not know, when it says register three, this register three, that's the who's getting it, that says I'm going here, somebody's producing it. Who's producing it?
Right.
It doesn't know.
Right.
How can it know who's producing it?
Can't be determined, right?
Yeah, this one, when it says, hey, send me your stuff, it has to send back and also over to here saying, who's producing it? This one can then track who's producing it. That's an optional extra thing it can do. You know, who's producing becomes an option. The standard one, you know, if it happens, it just X's an issue. If it doesn't get, right, so it'll get this X if it was successful. It gets an error back, it doesn't flag it. Because then it's got a reissue. So this is just lets it know, hey, do I need to do more work that's going on? But we can also have the optional thing to say, hey, number one is producing it. Right, reservation station one is producing the answer. But this one also needs to know it, coming back, so it can put the one there for who is producing. Does that make sense? So if you kind of think about what the algorithm has to do, like the book will give you all kinds of pseudocode and everything else that's going on. And if you look at it, when you first started looking at the code, I guarantee you it looked horrendously complicated. If, you know, once you start to get the idea of what is it trying to do, it actually really simplifies up. What makes up most of the room is you're having to check a whole bunch of places in parallel. That's actually where the majority of the complexity is. There's just a whole bunch of them that's going on to it. But you do want to think about who needs a piece of information so you make sure you route the signals to those locations.
So as far as design goes, it seems to me at least that the most critical part of this whole thing is the size of that queue and the functional unit.
Yes.
So, I mean, earlier we talked about increasing performance by getting more common data buses. Well, as far as cost and trade-off goes, would it make more sense to actually, instead of getting more common data buses, just put more money into the size of your queues and increase
So yes.
power that way?
So making the queues larger becomes important, and then you would typically want a lot more than we've got. I guess we're running out of time, right? Well, we can continue this next time too as it goes on. But that is an important question. Realize the queue size that I put in the labs 3 is completely stupid. Okay, it should not,
yeah.
it should not be
That was-
that.
that was part of my-
Small,
yeah.
it's not a power two.
That was part of my
It's
motivation.
small and not power 2,
Yeah.
right?
Yeah.
Should I do a power 2?
It could be convenient, I think.
Yes, you should
Yeah.
absolutely do a power
Yeah.
2, so why didn't I?
To make us do
To do the intro.
Artificial complexity, that's
Yeah.
the intro lab is exactly it.
Yeah.
I designed it for a different university where I had computer science people coming in, and they could have come from another university. And so about half of the grad students coming into that had never seen a hardware description language before in their life. So I needed a first lab that was really stupidly simple where I could introduce case statements, because most computer science people don't like case statements. They like if then else's, and to them, they don't see a difference. To us in hardware, it's a big difference on how they're built. It's huge. The case statement is crucial to us. So that becomes a really big feature that goes on. And so I needed something that handled all this, and if I had made it a power of 2, it would have been so stupidly simple, you wouldn't have to do any work, because the bit flags would automatically handle the roll, and so there would be no need to put in a check. You wouldn't need a lot of that hardware, it would automatically be handled. It's exactly that reason why you should do it, right? You should do 4 or 8 or 16, because it's just simple, you can strip bits off. I deliberately did it ugly so that it forced you to build that extra little unit in there. So, you know, that's the reason for that complexity. And I probably should rewrite the labs to remove it now that I no longer have that difficulty of people coming in who have never seen a hardware language before.
I still thought it was good, because I haven't used Verilog before, so it was at least a good.
So it was a kind of a helpful intro.
It was helpful.
We're switching to Verilog as it's going through, just because Verilog's a little easier to learn. You need both. Verilog and VHDL, indispensable. You need both. My belief is you do the easy language first, and then you handle the more complicated language, and you see why you need it, and you can adapt. Both of them, there's a small step to learn the next one, once you've learned one. And so then, in my opinion, you learn the easy one and make the small step, as opposed to learn the complex one and making a small step. So,
Do you think Verilog's easier?
yeah.
Oh, I think it is. I like it more than the HDMI personally.
Yeah, I mean, it's just easier because when you take an introductory class, what language do you learn?
C.
C or C++, and Verilog is based on C, C++. So therefore, it's got a heavier correlation with what's going on. So when I'm trying to teach you the concept behind an HDL, which is a little bit different than a programming language, I'm not trying to teach you syntax plus the concept of a hardware description language. I'm only trying to teach you the concept of a hardware description language. And the syntax is pretty darn similar, right? I mean, that really, to me, if people learned Ada naturally, VHDL would be the right one to start with. Because then Ada, VHDL is based on Ada. So if you came in knowing Ada, then VHDL would be a small step. Because that's what the syntax is based on. And I would just have to teach you the idea of that.
Does anyone even use Ada anymore?
There are some. It's a very, if you like, the military are the ones who really pushed Ada, and they're the ones who really pushed VHDL that was going on. But it has certain nice features inside. It's a very object-oriented language, so it's very strict. So when you're trying to build like data structures and things of that sort, it's got a lot of things to recommend it that's going on. In reality, you can make each portion of your project based on a different language. Right? I mean, there's no reason not to. Then you can program in whichever one is the natural one to draw it in.
Yeah.
I mean, and to me, that's really where it comes down to, is use the right tool for the right job. If I said, I need you to build a house, you know, do you want a hammer, a screwdriver, a wrench?
Blowtorch.
you know? Well, I mean, if you could only have one, you'd probably pick the hammer, okay? But there's places where you want the hammer, and there's places you want the screwdriver, right? I mean, you could go through, each one has their place. You know, I mean, maybe you say, I want the wrench, because I can tighten the pipes, and I can always beat a nail in with it, right? I mean, but, you know, while I might be able to use the wrench to do all those things, is it good? Or should you, for the job, pick the right tool out of the tool belt? I submit to you that languages are like that. So too are design methods. The more design methods and the more languages you know, the more tools in your toolbox. Right? So that's why you want to get the ideas and where are they useful for, and then you can use them efficiently. And if you decide you don't want to split them up and you're like, hey, I don't feel like going over and grabbing that thing because it's a tiny little thing, I can use my wrench to drive the nail. You know, but it was a tiny nail, and, you know, and I didn't want to go looking for the hammer. Okay, you know, I mean, maybe some people would hate you for that statement, but I think it's practical where it goes on. Right? If I'm hanging one little picture and there's a rock, I'm going to knock the nail in with the rock. I'm not going to go out to the shop to get a hammer. You know, but if I'm doing a bunch, I'm going to go get the right tool. And so I would just recommend that as it goes in. But by and large, I happen to like Verilog better. There's advantages to each language also. It's a little lower level. You can do, you know, some things more naturally in it. But each has their place. Okay, do we feel comfortable with this? We'll run through a bigger example next time. Do you mind?
I really want to know if that recorded everything.
We'll find out.
This course on Verilog